Next, we're going to get into kind of what I could think of as the heart of these series questions of convergence and divergence. And one thing that I cannot stress enough is that the answer is not nearly as important as the journey that you take to get there, especially with these kind of problems. I am not interested as much in whether you know the answer at the end of the problem as I am whether or not you know why that is the answer, and you know which test you use to verify it, and you understand how that test works. So pay close attention to this, because when you show your work for these types of problems on the final exam, I am going to expect to see which test you used and see that justification. So be very careful with this. So the first test that we're going to look at is called the integral test. If f is positive, continuous, and decreasing for x greater than or equal to 1, and a sub n is equal to f of n, then the sum from 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. Now this integral right here is one of those improper integrals from chapter 8. So remember, those integrals could either converge or diverge depending on what ended up happening. So this says apply the integral test to the series from 1 to infinity of 1 over n plus 3. So we're going to let f of x be 1 over x plus 3, and we're going to talk about this occurring for x greater than or equal to 1. So this thing is continuous because x is not allowed to be negative 3. So a couple things you need to check. Number one, 1 over x plus 3 is greater than 0 for x greater than or equal to 1. So we're good there. It's positive. Number two, 1 over x plus 3 is continuous. And again, that's for x greater than or equal to 1. So we're good there. Got continuous. And we need to know that it's decreasing. We need to know that for f of x is x. If x increases, then f of x is decreasing. Now you can do this with n's if you want to. So we know that n is less than n plus 1. That's obvious. And if you add 3 to both sides, it's not going to change that relationship. So now we know that if we have a larger denominator, then this with the same numerator on top, then the fraction of the larger denominator is going to be smaller. So what we have here then is a sub n plus 1 is less than a sub n. So we have that this thing is decreasing. You need to verify those three things before you use the integral test. So we can use the integral test. So I'm going to take the integral from 1 to infinity of 1 over x plus 3 dx. And if you remember how to deal with these, that's the same thing as taking the limit as b approaches infinity of the integral from 1 to b of 1 over x plus 3 dx. Now, this integral evaluates to be the natural log of the absolute value of x plus 3. And we're going from 1 to b. So we're going to have the natural log of the absolute value of b plus 3 minus the natural log of the absolute value of 1 plus 3, so that's 4. And if we plug in a b going towards infinity, this is going to be infinity because natural log is increasing to infinity minus a constant. So this thing is equal to infinity, and this integral diverges. So by the integral test, the sum from 1 to infinity of 1 over n plus 3 also diverges. If you get that your integral diverges, then the series diverges. If you get that your integral converges, then the series converges. With this one, we're looking at the sum from 1 to infinity of e to the negative n. So I'm going to take a similar approach. I'm going to have f of x equals e to the negative x, and I just need to verify those things. Is it positive for x greater than or equal to 1, and is it continuous, and is it decreasing? So number one, e to the negative x is equal to 1 over e to the x, which is greater than 0. So this thing is positive. e to the negative x is continuous everywhere. We don't have to worry about any discontinuities. And if I want to know if this thing is decreasing, I could take the derivative, which would give me negative e to the negative x with no discontinuities. And since that's less than 0, we can say that f is decreasing. So the integral test applies. So you can use that. That increasing decreasing relationship based on the derivative. If it's negative, it's decreasing. If it's positive, it's increasing. So the integral test applies. So now I'm going to do it. I'm going to take the integral from 1 to infinity of e to the negative x dx, which will be the limit as b approaches infinity of the integral from 1 to b of e to the negative x dx. To integrate this, my u would be negative x, so I need a negative here and here. And I get the limit as b approaches infinity of negative e to the negative x from 1 to b. So this is the limit as b approaches infinity of negative e to the negative b minus e to the negative 1. And so that'll be minus a negative, sorry. So this would be 1 over e minus 1 over e to the b. And as b approaches infinity, this is going to go to 0. So we get 1 over e and it converges. So by the integral test, we can say that the sum from 1 to infinity of e to the negative n also converges. Okay, if you are writing out your work for this problem, I do expect to see all of these steps, okay? If you're working in WebAssign, it may just ask you, does it converge or not? But if you're actually working through the problem, this is what's important. Can you work your way through this process? Another thing that's important to note is that the integral converges to this value, but that doesn't mean that that is the value of the series. That just means that it also converges. So the integral test doesn't give you the actual sum, it just tells you whether a sum exists or not. Okay, this example says explain why the integral test does not apply to the series from 1 to infinity of negative 1 to the n over n. So you remember that for all x greater than or equal to 1, f has to be positive, continuous, and decreasing. So if I were to allow, for example, n equals 3, negative 1 cubed divided by 3 is less than 0, so it's not positive. So we cannot use the integral test because it's not always positive. If it breaks any one of those 3 rules, you can't use it. One special consequence of the integral test we get are what are called p-series. A series of the form 1 over n to the p, which is 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, so on and so forth, is a p-series where p is a positive constant. For p equals 1, we're specifically looking at 1 over n to the first power. So this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, so on and so forth. And this is the harmonic series. A general harmonic series is going to take the form 1 over an plus b. Now this p-series test is a consequence of the integral test, and you can see that proof written out here if you want to pause the video and read through that. I'm not going to go into it in detail, but it is a consequence of the integral test. And it says that if p is greater than 1, then this p-series converges, and it diverges for p between 0 and 1. So notice that if p is equal to 1, this whole series has to diverge. It converges for p greater than 1. It diverges for p between 0 and 1. Now, this is going to look different from the geometric series we talked about last time. This is actually going to be backwards, because what's happening is if p is greater than 1, your denominator is growing in such a way that it's shrinking your function enough to force it to converge. So this particular integral test would allow you to do that. Whereas if you're not shrinking your denominator enough, it might not work. So let's discuss the convergence or the divergence of the harmonic series. So this is the sum from 1 to infinity of 1 over n. And we know that that's 1 over n to the first power. So this is a p series with p equals 1. And that is less than or equal to 1. So the p series test says that this will converge, or this will diverge. Notice that the limit as n approaches infinity of 1 over n does go to 0, okay? So that's an example of why the nth term test cannot guarantee convergence. It can only guarantee divergence. So you'd have to use the p-series test here. All right, if p equals 3, we'd be looking at the series from 1 to infinity of 1 over n cubed. P equals 3, which is greater than 1, so this converges. Again, we don't know what it converges to. We just know that it does converge, and that's all we care about. Okay, this one is a p-series in disguise because this could be written as the sum from 1 to infinity of 1 over n. This is the 5th root of n, so that'll be n to the 1/5 power. So p equals 1/5, which is less than or equal to 1. So the series diverges by the p-series test.